welcome to Friday's edition of Cracking the Cryptic, where today I've been asked by Mark to load in today's puzzle actually live on camera. So that's why this puzzle on the screen may look familiar to you. This is yesterday's Fairy Rings puzzle by Jay Dyer, which is an incredible Sudoku. Do check that out if you haven't had a chance to look at it yet. But I'm going to load up today's in just a moment. Before I do that, I want to say very well done to one more person who managed to squeeze in before the deadline on the Star Wars Sudoku hunt. So well done to Tom Van Verkum. Your entry appeared with 12 minutes to spare yesterday, so you were included in the draw to win the prize, but the prize was won by Jose Cusco. So Jose, your Bubba is You key is already in an email to you, so hopefully you've received that. Very well done. And yeah, what have we got coming up for you on Patreon soon? We've got loads of stuff. Well, firstly, we've got my solve of what's it called? Fillomino Aquarium by Phistomefel. One of the most extraordinary puzzles I have ever solved in my life. That is available right now. Mark is releasing his latest solve of the Times Club Monthly Special Cryptic Crossword in the coming couple of days, so look out for that if you like the cryptic crossword content. We've got the solution videos for the Star Wars Sudoku hunt also coming up imminently, and then on the 1st of February we have what we're calling our QAS, quite approachable Sudoku hunt. So we've got that coming up, which features a number of different puzzles, which are all slightly more difficult than gas, but not sort of monstrously hard. So we hope that will suit all of you. Now, with all that said and done, let's get on with launching this puzzle. I'm slightly worried about this because the last time I had to open a puzzle on the screen, it turned out to be SUDOKU, which then took me about 2 hours to solve it. So let's have a look at what we've got today. We have got Boomerang 2 by Ard van der Wetering from the Netherlands. Ard, of course, is very well known to us on Cracking the Cryptic because Ard is responsible for the puzzle behind our biggest ever video. It was the video we called a Sudoku with only 4 given digits. This one only has 3 by the looks of things. In fact, well, hang on a minute, let me just read the rules of this. But that video has been seen about 8 million times, believe it or not. 8 million people have watched me solve a Sudoku. That is a very strange thing to say. Right, and this is a very strange puzzle because this appears to be normal Sudoku just with 3 arrows and a knight's move constraint. That's ridiculous. Okay, so yeah, those of you who might have been with us since the Miracle Sudoku will remember that although the Miracle Sudoku had 2 given digits, it had Knight's Move, King's Move and non-consecutive constraints as well. Here we have just a Knight's Move restriction and 3 arrows. That is weird. Okay, well, let's get on with it and read you the rules. It's called Boomerang 2. So normal Sudoku rules apply. Digits along an arrow must sum to the digit in that arrow's circle. So that means those 3 digits there, you add them up, and whatever these 3 digits add up to, you put in the circle. Cells separated by a knight's move in chess cannot contain the same digit. So imagine that cell was a 1. That would mean that a chess knight in this position could jump to these, let's try and get this right, these cells, and therefore none of these highlighted digits could be a 1. Because if they were, they would be a knight's move apart, and that would break the rules of this puzzle. Do have a go at this puzzle. The way to play is to click the link under the video, as usual. Now I get to play. Let's get cracking and see whether this is indeed solvable. I mean, it will be. Ard is an absolutely incredible setter. And he's not normally monstrously difficult, but he does have some very weird ideas from time to time. I mean, these given digits, I mean, the 4 and the 5 can be ruled out of these 2 squares because of the knight's move constraint. You obviously can't have a 5 there. See that one by knight's move. Same with 4. But I can't see anything. I mean, these arrows have to be at least 6, don't they? And that's because in each case we've got 3 different digits on the arrow, and the minimum you can make 3 different digits add up to is 6 with a 1, 2 and a 3. So these are at least 6. Yeah, okay, and whatever goes into this arrow circle Where can that appear in box number 8? Well, by Sudoku it can't go there. It could never appear on its own arrow because you've got to add 2 digits to that digit in order to end up with the circle. So the only way that would work is if you added 00. And it can't go in here by knight's move. So this cell has to go in one of those 2 cells in box 8. And presumably that logic is repeatable because of the symmetry in various other spots around the grid. So let's try and at least do some highlighting. So those positions are restricted. And I guess, well, also I better give these a flash to indicate that I don't know which of these is the green cell. It's one of those 2, but I don't know which. Now, okay, right, I see. Right, what about this cell? Where does that cell go in the central box? That's on the arrow. It's on the purple arrow. So it cannot be. Well, the maximum size of a digit that's on a 3-cell arrow is 6. If we try and put 7 here, 7 plus 1 plus 2 is 10, and we can't put a double-digit number into a Sudoku digit. So this cell is a maximum of 6. Now, rather annoyingly, if we think about the knight's move constraint and where the orange digit can go in box 5, it can't go in those 3 squares by Sudoku, and it can't go in these 2 squares by knight's move. It could go in a circle, but only if it's a 6. And that would make this arrow into a 9 arrow. So if that's a 6, you have to put 9 here, because the minimum you could put on the other 2 cells on the arrow would be a 1-2 pair. So if this is a 6, one of these 2 would have to be a 6. And a 6 arrow needs a 1, 2 and a 3 on it. And if this cell is not in a circle, it has to be exactly here. Right, I see. I see, Odd, what you're up to. Ha ha ha. Now I want to look at that square and ask where that goes in box 5, because the same logic exactly applies to this square. But it's not possible for both of these cells to be a 6. Self-evidently, they're both in column 5. So one of them must go here, in the box. So that cell is either yellow or orange. But does that mean one of those? It does mean one of those has to be a 6. They can't both. This is not a Schrödinger cell. So if we try and put 2 here and 3 here, and then ask where 2 goes in the box, it would have to go here, and where 3 goes in the box, it has to go here. Well, that cell simultaneously cannot be 2 and 3. So one of these squares is definitely a 6. And one of them, which could be a 1, 2, 3, 4, or 5, goes here. That's really peculiar. So that means that as there is a 6 in one of these arrows, one of these is a 9 arrow, because we know that wherever the 6 goes in column 5, it's on a 1, 2, 6 arrow, which is adding up to 9. So that cell is not a 9. Now we know that this arrow has a 1 on it, because it's either, if it's 6, it's 1, 2, 3, if it's 7, it's 1, 2, 4, and if it's 8, it's either 1, 2, 5 or 1, 3, 4. This is a fascinating puzzle, isn't it? It's very... I mean, how do you come up with these ridiculous ideas for putting puzzles together? Okay, now come on. I think we're one deduction away now from figuring this out. If we have... So one of these arrows is 6, 1, 2. And whichever one it is will have a 1, 2 in the sort of stubby end. Now the other one... Yes, we now know that there's a 6 arrow, of course, don't we? We know there's a 6 arrow because this 6 has to appear in one of these squares. So one of these arrows is a 1, 2, 3 arrow. But is there any restriction on which one it is? Obviously it's not the one that has the 6 on it, so if that was the 6 you couldn't put the 6 here, but I think either of these could probably be the 1, 2, 3 arrow. Ah, this is... how on earth do you... Okay, that's not good. Can you... if that was a 6, 9 pair... if that was a 6, 9 pair, you'd get a 6 in one of those. Now, oh no, I was about to say maybe you could do something with the 3 here, but only if that's a 6 can you do something with a 3. That would be a 3, that would be a 1, 2 pair. That would break, in fact. I think. This is very peculiar and a bit bifurcated, but I can see it, so I'm going to allege it's not bifurcation. If these were a 6, 9 pair, and you try and put the 6 here, then this arrow is a 1, 2, 3 arrow. The 3 on it has to go here, and this has to be a 1, 2 pair. But this arrow is a 9 arrow with a 6 here, and this is a 1, 2 pair. And now, where do you put 1 and 2 in column 6? They have to both be in simultaneously in that cell, and that's not okay, is it? So, but if that's 9 on the other hand, and this is 6, this could absolutely be anything, and that totally blows that out of the water. So that's fairly actually not helpful. Wow, okay. So am I on the wrong track here? If this isn't... Ooh. no, come on. Well, I'm now wondering whether I need to think about this totally differently, because this is not working. I'm now thinking whether it's a set puzzle, because that is my experience when when I think things are too minimalistic. It tends to be set, doesn't it, that gets you out of trouble. But it's not very easy for me to see. In fact, what I'm going to do to even investigate this, I'm going to duplicate the tab, if that's all right, and get rid of my highlighting, because I find it a bit difficult to see set things when I've already got the highlighting in the grid. So if we're going to try and do something set related, we need to put all of these circles in a different set to the arrows that they have emanating from them. So it looks like it's... yeah, even that's quite hard to do. Is it this box versus that column, this row? I'm just going to look at that. Let me have a quick look at that, and then we can see. So if we do that and those two as a different set, this is double orange. I will explain this if I think this is going to do anything, by the way, so do not worry. So then we have got the ability to do some cancelling here. Although it's horrible cancelling, because these little arrow tips are all not in a set at all at the moment. So if this was right, and we tried to do some sort of cancelling down, we'd take this out of the blue set, and then we would have to take those two only out of the orange set, which would under-deduct from the orange set by the amount of this square. So this... yes, okay, so that would remain in blue. Yes, if you cancel those out, you get left with that, don't you? So these would remain in blue, but these would all disappear from blue. Let me just have a look at that. And we will then, I think, abandon this because this feels a bit too mad to me. So then, what have we got now? Originally we had 2 lots of orange and 1 lot of blue. So we've got 45 more in orange. So blue plus 45 equals orange. Orange could be 35, 17, 52. Oh, for goodness sake. Wow. Okay, that is... Wow. That is... Well, yes, that is wow. Jeepers creepers. Okay, there may be a simpler way of doing this, but we have found a break-in. Let me go back and let me explain what on earth I've just been doing. So what I did was I highlighted box 5. So you remember, what I wanted to do was to find some sort of offset between the arrow cells and the circle cells. So I started off with box 5. Now, these digits here are one set of the digits 1 to 9. I've got no idea what the order of these digits is, but I can describe them in total as one set of the digits 1 to 9. Now, I want to consider what this set would be. So imagine we've got a blue bag full of Scrabble tiles with the digits 1 to 9 on it. So there's a blue bag here, and I'm going to have an orange bag with these Scrabble tiles on it. We did set yesterday, didn't we? So we're doing set again today. So that's clearly one set of the digits 1 to 9 as well. So we could plonk these digits into our orange bag. We'd have 9 tiles in my orange bag, 9 tiles in my blue bag, and at this point the bags contain the identical contents. They contain 9 Scrabble tiles, and each Scrabble tile there'll be 1 Scrabble tile with a 1 on it in the orange bag, and one with a 1 on it in the blue bag, etc., all the way through to the Scrabble tiles that contain the 9. Now I'm going to add 9 more Scrabble tiles to my orange bag, because I'm also going to include this row of digits. That's a complete row of the Sudoku. So again, it's one set of the digits 1 to 9. So this digit, whatever happens in the middle of the grid, that digit is in my orange bag twice. Actually, it's on 2 different Scrabble tiles. So let's just highlight that in orange, noting that this one is this one with the purple flash. That's double orange. That's in the orange bag twice. So I've now got 18 Scrabble tiles in my orange bag and 9 Scrabble tiles in my blue bag. Now I can go and hunt for digits like these 4 digits. So let's imagine that digit was a 4. If I go and find the 4 in my blue bag and find a 4 in my orange bag, and I take them out of both bags and throw them away, then well, let's actually start before I delete this 4. I've got 18 tiles in my orange bag and 9 tiles in my blue bag, and the difference between those 2 bags is one set of the digits 1 to 9. I think we could agree with that, because I've got 2 complete sets of the digits 1 to 9 in orange and only 1 complete set of the digits 1 to 9 in blue. So if I remove the same digit from the orange bag and the blue bag, i.e. whatever's in that square, doesn't have to be a 4, it could be any digit, whatever is in that square, I'm saying I'm removing it from both bags. When I've done that, the difference between the bags is still one set of the digits 1 to 9, because the difference between the bags before I did anything was one set of the digits 1 to 9, and I've just taken the same thing out of both bags. And I can do that for any of those cells. This cell is a little bit more complicated, because this cell is the digit in this cell is on 1 Scrabble tile in the blue bag, but it's on 2 Scrabble tiles in the orange bag. So once I cancel this out, I can get rid of 1 blue and 1 orange, and this is left to be orange. And at the moment, it looks like madness. Why am I doing this? Well, the reason I was doing this was what I wanted to do was to try and find some sort of equivalence between these lines. And this is where it gets really interesting. Because if I sum, at this point, the difference between the blue bag and the orange bag is still one set of the digits 1 to 9. And that means, if we think about it a bit further, because of the secret, the digits 1 to 9 if you add them up, they add up to 45. So, we could describe the difference between the blue tiles and the orange tiles as being the blue bag plus 45. The digits in the blue bag, if we add them up and then add 45 to it, we will get the same as the sum in the orange bag. So, if I was to remove this cell, whatever the digit is in this cell from the blue bag, and I then removed those two digits, whatever is in those two digits from the orange bag, we've got a problem now, because I haven't removed the same thing from both sides of the equation. This definitely adds up to more than these two, by whatever this digit is. So in order to preserve the relationship that I want to preserve, which is that the blue bag is different from the orange bag by 45, I have to, if I remove this from blue and these two from orange, I have to restore this digit to blue. And you can see that probably if we do an example. Let's imagine that's a 9, and this is, let's imagine it's 612 actually. Let's do that. So, if I remove 9 from my blue bag and only 7 from my orange bag, then I need to put 2 into my blue bag again in order to say that the difference between the bags is still one set of the, well, not one set of the digits and one set of the digits 1 to 9, but the difference between the bag is still a total of 45, and that's what I'm trying to do. So what we're going to do is exactly that. We've got no idea what's actually on this arrow. We've got no idea what this circle actually is in the finished grid. But I know if I remove this digit from my blue bag and these two digits from my orange bag, and replace this digit into the blue bag, whatever it happens to be, at this point it is still true to say that the difference between the blue bag and the orange bag is 45. And I can do that here, if I put that back in blue, and here, if I put that back in blue, this back in blue. And you can see it's now becoming clearer to me why Ard has done this. It's really clever. It's really clever. And in a way, I've lucked into this, because what I tried to do was to just find a relationship that put the arrows on into different colours. But now consider the shape that Ard has used. So Ard has put these arrow tips in the same column of a Sudoku, which means that these 3 digits now all have to be different digits. And this is where the magic is going to happen, because at this point, due to all our chicanery, we have a relationship between the blue cells and the orange cells. The blue cells plus 45 equal the orange cells. Well, what's the maximum value of those orange cells? 5, 6, 7, 8, and 9. You couldn't put more than that in them. 5, 6, 7, 8, 9 add up to 35. What's the maximum I could put into those two cells? Well, that would be an 8, 9 pair. That's 17. So 35 plus 17 is 52. But we know that blue plus 45 equals, therefore, a maximum of 52. Which means that blue is an absolute maximum of 7. Well, because these are now all in the same column, the minimum they can be is 1, 2, 3. And the minimum this can be is 1, and that means 1 plus 2 plus 3 is 6, plus 1 is 7. So it's utterly forced. It's utterly forced. And it's the beauty of these arrow tips that does it. Because if these arrow tips, imagine this arrow tip here had gone this way, and this arrow tip had stayed the same, then you couldn't have said that these have a minimum value of 7, because this could have been a 1, that could have been a 1, that could have been a 2, and that could have been a 2, and you could have added them up to 6. In fact, you might have even been able to do better than that. If you go double 1 here and 1 here and 2 there, you could get them adding up to 5. So it's the genius of this. Well, the whole thing is the whole conceit of this is ridiculous, isn't it? That the structure inherent in this Sudoku allows this sort of mathematics, which forces this. I mean, that is a 1. That's what we've just proved. This is a 5, 6, 7, 8, 9 quintuple. That is a 1, 2, 3 triple. And that's not a 1 because it sees the 1 we've just put in. Those aren't 1s anymore. Now I'm wondering actually whether I should go back to my old grid. Ooh, or should we stick with this one? Let's just have another look at my old grid though. Because now, what are we saying? We're saying that, you see, it's going to, yes, it is confusing actually. So what have we got to remember? What did we learn before we did our set? We learned that these 3 digits were all limited in their adjacent boxes. Oh yes, and we learned that there's a 6 in one of those 2, and that this digit is also appearing. Right, let's go back here. So this digit, so now I know these are a 2, 3, 6 combination, because I know that whichever one of these is not 6, it's plonking a 2, 3 in here, a 2 or a 3 in there. Okay. Oh, right. In fact, look what we can do now. This square is a naked, that's a beautiful, beautiful naked single. It sees 1, 2, 3 in its column and 5, 6, 7, 8, 9 in its row, so that's a 4. So now what does that mean? Oh yeah, okay, now, no, a simpler question now is where does 1 go in row 5? Let's actually do Sudoku. That's a 2, 3 pair now to complete row 5. 1 plus 2 plus 3 is 6. We can write 6 in here. So that, right, okay, so this didn't end up being a 6, 9 pair. I think the only way it could have been would have been the 6 on the top and the 9 below. But actually that's been blown out of the water now. That sees an 8, 9 pair in its column, so that's 5, 6 or 7. It's not 6 anymore. So we've got 7s, 8s and 9s here. Oh, come on, Simon. What can we do next? Wouldn't it be, well, it would be awful if I can't solve it, having come up with that break-in. Oh no, this square can't be a 3 because it sees this 3 by knight's move. So we've got to work out what's going on. What have we got? What have we got? 4. Oh, okay. Where does 4 go in box 8? I think Sudoku is going to be very important now. So that square's a 4 in box 2. And that's on an arrow. Right, here we go. Right. So now we've got a 4 here. So that can't be on an arrow with a 6, or this would have to be at least 10 or 11 if that's a 1. But definitely it's broken. So the 6 is not here. And if the 6 isn't there, we know the 6 must be here from the work we did earlier, which means this must be a 9 arrow, which means this is a 1, 2 pair. Good grief. That's no longer a 9. So this is 7 or 8. Now, what does that mean? Probably something very profound. If this is 7, this has to be a 1 here and a 2 here. If this is 8, this has to be 3 here and 1 here. Is this always a 1? Is that what? Yes, okay, yes, this arrow is either a 7 or an 8, so it must have a 1 on it. The 1 must go up there. So that becomes a 2, that's a 1, that's a 3. Yes, oh, this is lovely. Okay, so now I ask where 3 goes in box 8. And it's got to go in exactly the same positions as 4. So that becomes a 3, 4 pair. That becomes a 3 by Sudoku. This arrow adds up to 8, so that's an 8. 8's in this domino. Oh no, it's not. Hang on, that's a mistake. That can be an 8, absolutely, because it's got 8 and 9 in the middle of its box. So we don't know what's quite going on there. What do we have? We've got to put 2s, 5s and 7s in the middle box. 5? Where does 5 go in box 8? It's got to go here by Sudoku. That gets a 7 in the middle of the grid. Oh, this is just wonderful, isn't it? There's a 5. Whoa, 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 whoa. There's a 5 up here. 5 up there, Simon. Do Sudoku properly. 7s, 8s and 9s into these 3 squares. is anything seeing any of those? 7 is seeing that one by knight's move. Oh, hang on, 7 and 8 are seeing that one, so that's a 9, I think. And that's beautiful. That gets me an 8 at the top, a 9 at the bottom. So that becomes a 7 by Sudoku, and that becomes an 8 by Sudoku. That should become a... oh, what's that digit? 7, that's okay. Okay, so we're still in the race. We are still in the race. We need 2s, 5s and 6s into these squares. 6 sees that one. I mean, actually, though, it's quite remarkable that this solves from here, because there's almost nothing. Well, there is nothing. There is nothing about these boxes, and very little about this box that we know. So there's still some magic going on here. 3 sees that by knight's move, so 2 and 3 can go in. 5 is in one of those squares, so it's ruled out of this square by knight's move. 8 and 9 are ruled out of that one by knight's move. So this is down to just 5 or 6. 3 is in a domino at the top of the box. 1 can't go in those squares, look, because of this one here. So 1 is in one of those 2 squares in box 7. Oh, that's lovely. Okay, so where does 1 go in column 3? Can't go here, can't go here because of this 1 and the knight's move constraint. So that becomes a 1. 1 can't go there by knight's move. So 1 is in a domino in box 3. Now that's actually interesting, because this little 1 in box 8 can't go in those 2 squares. So 1 in box 9 is in one of 4 positions, but critically it's definitely not in column 7. And you can see now that the 1 in column 7 actually only has 1 available place, which is there. Which resolves where the 1 goes in box 3, because these can't be a knight's move apart. So that becomes a 1. 1 comes out of those, and we're left with a sort of X-wing pattern on 1s at the bottom of the grid. 2 is placed in box 7 now. Just this 2 is doing mighty work. It rules itself out of those 2 by knight's move and that by Sudoku. So actually we could have just placed the 2 down there if I'd looked at that earlier. 2 is placed in box 1 because 2 can't be a knight's move away from itself. So 2 in box number 3 is apparently not placed, or not even pencil markable, which is a bit frustrating. Okay, so where do we look now? Have we got more? Yeah, hang on, we've got loads of stuff going on in row 8 now. That is a 6-9 pair. Is that helpful? Not sure. No, sorry, I'm really not sure actually. 3. This 3 is seeing that square, so we get another couple of digits as a result of this. 3 must be in this domino in box 9. 4 is completely, it's completely unrestricted in box 7. Yes, this is what I feared might happen actually here. So 6 is in one of those 2, which is the corollary of the colouring we did earlier. The 8 and the 9 we've already got from there. So 6 in column 3 is nearly restricted enough. It's either here or it's here. But I think either of those is possible, which is very annoying. So how on earth do we make more progress? That's the question. And the answer is I've not got a Scooby-Doo. Wow. Where should I even look? Let me adjust my seat position and see if I can see something. can we do anything with anything? It must be. Oh, actually, I don't know. I really don't know what it is. It's going to be some weird Knight's Move thing. Probably around either this column or this column. Although that, I see digits like this are a little bit interesting because they see the whole of that triple. So that can't be 2, 5 or 6, and it can't be 4 or 7 or 1. So this digit has to be 3, 8 or 9, I think. So there's probably ideas like this that we need to take advantage of. 3, ooh, yeah, good grief, yeah, okay. Let's ask where 3 goes in this column. This 3 takes care of those squares. This 3 takes care of that square. This 3 takes care of those 2 squares. So 3 has to be here, which means we get another 3. How many 3s have we got? The answer is nearly all of them. We need bobbins. We need 1 here and 1 here, and I don't think we're going to be able to disambiguate that using the information we've already got about 3s. So we're going to have to come up with something else. But it's going to be something like that, isn't it? So which other digit is going to be restricted up this column? Is it, I don't know, or maybe this row even? 2, 5, 6, 8, 9. 2, 5, 6, 8, 9. That square does see 8. Oh, we're going to get into mad pencil marking here, though. Okay. All right. Come on, Simon. There must be more we can do. 6 is... Oh, no, I've already looked at 6. I've even spotted the deduction regarding 6. It's in one of those 2 cells. I've already spotted that. Don't think about the same things twice. That will not help you to solve this. Is 9 restricted? 9 is a bit restricted in this column. It can't go there, can't go there, and it can't go there, but I think it's still got 2 available options. Hang on, what can that digit be? That digit can't be 1, 2, or 3. It can be 4, but it can't be 5. It can't be 6, 7, 8, 9. Oh, good grief. Right. That is a naked single, believe it or not. By which I mean, if you actually investigate what this cell can be, taking into account all of the various Knight's Moves things pointing at it, its only option is to be a 4. That's absolutely evil. Okay, but that's useful though, isn't it? That gets us a 3, 4 pair over there, which might be helpful. So I think, yeah, okay, we're going to have to pay particular attention to this column. We've now got to put 6, 7, 8 on. Oh, right, that's a 9. See 6 and 8 in its row and 7 in by Knight's Move. So that's a 9 now. So the remainder of this column needs to be 6, 7, and 8. Where, oh, bother. That one can't be 6. Can we do better than that? Probably. There's probably something looking at these. Can't see what it is though. I feel like this one's resolved for some reason, but I can't see how. Okay, so let's think again then. So this square here now is no longer a 9. So, oh no, that doesn't work either. Okay, so the 9 is in one of these 2 squares in box 6. Jeepers creepers. Where does 6 go? In row 6 of the grid now. Now, this 6, 9 is beautiful because it rules a 6 out of either of those because of the Knight's Move constraint. This square can't be a 6 by Knight's Move. So I think that's the only place for a 6. Which means that's no longer a 6. Don't know if we can eliminate 6 from any of these squares. I'd love to do that. So these are 5s, 7s and 8s, I think. Golly, it would be really nice if I could resolve these, wouldn't it? Have we got, is there some knight's move that's helping me to do that? I can't see it. Or maybe we can get 6 down here. 6 in box 7 is what I'm wondering about. This can be a 6, I think, or this might be able to be a 6. At least it's locked into one of 2 places. Oh, which it was anyway. Oh, bother. 9 is in one of those 2 positions. In box 7. Oh no, it's still not going, is it? Okay, what about these squares then? Oh, hang on, I've got 8 here. So that place is 8. Never mind the 5 in this box. Where does 8 go? It's got to go here. That means I can actually get a triple in box 6. I get rid of 8s from these. This is a 5-7 pair. Now I get the centre done. 2 and 5 go in. 2 comes out of this square by knight's move. I've got a 5-6 pair here, so that places 2 in the column. It's got to go there. So 2 is locked into one of 2 places now in box 3. And these squares are now known. They've got to be a 2, a 7 and an 8. And I can immediately see, because art has made me learn, that this square here can't be 7 or 8 because of the knight's move. So that's a 2. This is a 7-8 pair. That fixes the 2 in box 3. Fixes the... beautiful. Look, it fixes the 2 in box 9 to this square, and because we have been diligently pencil marking away, look what this does. It takes the position of a 3, so that now is the 3, and that forces the 1 down here, which forces a 1 here and a 9 here. So this feels like real progress all of a sudden. That 3 is doing a 3 and a 4 in, and that's placing a 4 up here, which means there's a 4 in this domino in box 1. Come on. This is exciting now. I feel like we might have a chance of solving it. So 5s, 7s and 8s are the remainder of this box. And that can't be 5, obviously. So there's a 7-8 pair left. But I don't think this one is seen by knight's move. Might be wrong about that. I sort of want to be wrong about it. That's not 7 by knight's move. 5. Oh, hang on. How can that be 3, 8 or 9 when there's a 3 looking at it? Sorry. That's 8 or 9. Yes, okay. So now the question is, where does 7 go in that column, I think? It's not here. It's not here. It's not here. And it's not here because of the knight's move. Wow. So that's 7. That's 8. Now, can we make use of this 8? Yes, this 8 seeing that one by knight's move. So 7 goes in the grid. 8 goes in the grid. So this is no longer a 7. We've got a 5-8 pair down here. 7 must be in one of those 2 cells. Again, it's probably resolved, but I can't immediately see how. And do we check this column for more jiggery-pokery? 5, 6, 8, 9. I can't quite see whether we can do better. Let's just put the options in and see what we can eliminate. I can eliminate 8 from this one by knight's move and 9 from this one by Sudoku. 5. Can I do 5 with anything? No. 5, 6, 8, 9. So this, that square sees 9 and 6. So that's 5 or 8 in row, whoopsie, in row 2, column 2. No, it's not 5. There's a 5 in this domino. So that sees that. So that's 8, I think. Which means that's 9, that's 5, and that's 6, and that's 5. That gets that gets 5 and 8 done in that column, meaning that's a 6 and that's a 9. Now, has that helped me? The answer is maybe. Yes, where does 8 go in box 3? It's got to go here. That's a 7. This column should be done. Yeah, 9, 6, 6, 5. Great. Okay, so now we need 6 and 9 here, which must be this way round, which makes that 7, that's 6. This 7 sees that square, so that's 5, that's 7. 7 needs a home here, that's 4, that's 4. And if I've not made a mistake, that's 5. Wow. Wow, wow. Oh no! What have I done? I've made a mistake. I've got 8s and 5s in the wrong places. Oh, you absolute thingy of a thing. That might be resolved. Was that quite a late thing I did? Yeah. Oh, yes, it was. Okay, so what on earth did I do then? I put 8 there. Oh, there's another 8 in this column. Oh dear, that's not good. That is not good. There needs to be an 8 in this column. How on earth have I made that mistake? That's a big reversal that's needed, isn't it? This is something the computer allows us to do. So, what did I do here that was erroneous? I placed a 7 in this column. That looks correct to me. But that's going to give me this awkward 8, which I don't like the look of. So that looks okay. That looks okay. 6, 7 pair, 5, 8 pair. 7's up there, looks correct. 5, 6, 8, 9, 5, 6, 8, 9. Is that right? I think so. I got rid of something from this square. Hang on. Let's have a look at this one again. 5, 6, 8 or 9. It's not 8. Why did I think this was... What did I do? I took 6 out of that as well. How did I do that? Maybe this is where I went wrong. 5, 6, 8, 9 here. That shouldn't have 9 in it. 5, 8, 9. Hang on a minute. Let me just think about this. Why did I think this couldn't be a 6? I don't know. That's really strange, isn't it? Why did I do that? I'm so sorry, everybody. I really am. That's appalling solving. 5, 6, 8 or 9. I don't know what I did, but anyway, that's 5, 6 or 9, I think. And maybe this will help, because then I started to look at this digit, didn't I? And this digit needs to also be 5, 6, 8 or 9. Now it can't be 5, I remember that. It can't be 9. So 5, 6, 8, 9. It's not 9, it's not 5. It's 6 or 8. And it's C6 in the column, so that's 8. I can't remember if that's what I had before. So that's 9. So now I've got a 5, 6 pair here. This 9 is doing some work down the column. Gets me a 9 and a 6 and a 5 and a 5 and an 8. So that's all good stuff. This 5 is getting me a 6 here. Ah, well, I ruled a 6 out from that square, so that was my error. Probably. That 6 is getting me 9 and 6 here, so that's getting me 8 here. Okay, so what do we need in this column? This is the wonder of computers, isn't it? If you'd done that, if I'd made that error, in a competition, that would never have been recoverable. But here, it might be recoverable. Let's hope so. Okay, so now it looks like we need 5s, 7s and 9s. Well, I can see 9 in the top row can only go in one place. So this square becomes a 5 or a 7, and that gives me a nice looking 5, 7 pair in column 1. So now we need 4, 6, 4 and 6 into these squares. Oh no, maybe it's going to stay difficult now. It can't, can it? It must be resolved. Why is this not? Oh, this 5, that's why. So that's 7 and that's 5 and that's 7 and that's 6 and that's 7 and that's 4 and that's 4 therefore, and that's 6 and that should be 5. I think I did have 5 in there, and maybe this is correct. Yay! Sorry about that. Complete ricket at the end. These things happen. I hope you'll forgive me. I'm not actually that disappointed with that solve, because, I mean, the break-in step is really clever. And it took me ages to even have the idea to think about it. So I've gone off on a bit of a red herring wild goose chase there for about 20 minutes probably, before I had the right idea. But what a beautiful idea. What a beautiful piece of setting again from the master. Just extraordinary. A lovely idea, executed with aplomb. You couldn't ask for more. And even after you get that done, some of the knight's move spotting is, well, it doesn't play to my strengths anyway, even though I've done probably thousands of knight's move puzzles in my life. But yeah, thank you for bearing with me. And we'll be back later with another edition of Cracking the Cryptic.